Hello. Oh, oh, wow. Surprise. Good afternoon. Okay. Good. All right. I'm going to do it. Okay. I never know which. Okay. I'm going to do it that way and then that way. That is to say, hello, Vivian. Hello, Gabriella. Hello. Hello, Vivian and Gabriella. And then hello, Michaela, Alyssa, Shagupta, she. I'm going, in order of visual or descending order of visual complexity. And Jayla, excuse me, and Mark, hello, hello, hello. And now I'm going to do, yes, indeed. And now I'll go in order of verbal, blah, blah, blah. So good afternoon, Alyssa. Hello, Jayla. Oh, Jayla's up there with the double. Okay. Good afternoon, Charlie. Good afternoon, Vivian. Good afternoon, Jaylyn. Good afternoon, Brenda. Good afternoon, Andrew. Good afternoon, Michaela. Hello and good morning and visualization, she. Good afternoon, Catherine with an I. Good afternoon, Lakshmi with an I, with a me. What's the oops? I mean, oh, yeah. Okay, good afternoon. Yeah, time, whatever. I mean, you know what they say, she and everybody, you know what they say, those who can't do, teach, and those who can't manage space and time teach physics or something like that. Anyway, good afternoon. Yes, Professor and lobsters. Yeah, I have to bring you, I have a stuffed lobster for you guys that I got to bring you before the semester ends. Hello, Shagupta. Nicholas. And whoa, that's cray cray. Get it? Cray, like the land of gaslighting. That's so harsh. Good afternoon, Mark. Oh, I can't even see that. Those are hands, right? Okay. Hello, Celine. So, I tried too hard to pronounce it. Good. Hello, Celine. There is no it's a social construct. Well, it is a construct, but a social one. Boy, that's interesting. Okay, and I will bring in the plushie. That's the word I'm looking for. Plushie, right? I will bring it in. I will. And good afternoon, Stephanie. Okay. Hello. Everyone, good to see you. It was good to see some of you yesterday. I mean, all of you that I saw, it was good to see all of you that I saw. If you know what it wasn't only good to see some of the people that I saw, but only some of the people did I see. Okay, sorry. Hello, I'm glad you're all here today. Actually, you can even remind me. We have things to do and stuff. And it really was, as always, a delight to see you guys yesterday. And it really did remind me of how much I'm not going to like it when I don't see you anymore in any form. So I do hope you bother me with letters of recommendation, requests, and things like that in the future. No, it was my pleasure, really. But wait, oh, whatever. Yeah, no, and I totally told you they were definitely not happening by today. Or did you not show up to that class? No, I didn't even pretend that they're coming today, Nick. But wow, what, you're not being mean. Wait, are you being mean? No, you just okay. Anyway, okay, yeah. So hello, okay. So hello, everybody. We are going to do some physics now. We're not dealing with midterm. We're going to do some physics. We're going to change things, but you're also going to remind. I know other things are going on in people's lives and in the city, and I did hear from a lot of you yesterday about that, and I don't know exactly what to say. I don't really want, but I get that reality is, that physics is not the only part of your reality right now or anyone's. And I do mean that. We are going to do some physics for right now, but we're also, you can please remind me, fair enough. Okay. You can please remind me to speak English. You can please remind me, please, that we are going to go a little bit early today, for reasons on my end and maybe on your end. So you can remind me at 1 to start wrapping things up. I'm not saying we're leaving at 1. I mean, normally we go to 1:30, obviously. I'm not saying we're going to leave at 1, but you can, if I'm starting to foam, if I start to foam at the mouth as usual, around 1, you can remind me that I said we're going to go a little bit early today, and I will start wrapping up. And again, I don't know how early is early. It might only be 10 minutes early, but I'm going to try to get us out of here a little bit early. So anyway, you can see I'm already, so feel free to remind me at one that I said that. Wait, oh, that's funny. Well, they don't need to know that you like, well, just turn me off and start watching a YouTube. It looks the same. No, they won't know the difference. Okay. But okay. So physics, actually, I can't help asking. Okay, we are going to talk about physics now, but before we talk about the physics that we're going to talk about, I actually, because you are you, because this is this class, I can't resist asking one thing about physics, but on a different topic. In terms of the Doppler effect board meeting that you had yesterday, and I do understand that many of you weren't there, and I totally get that and all of that. And I'm pleased that you're with me here now in this Zoom time. Like, but those of you who were there, I just have a question, because I do love the Doppler effect, and I love that you're doing that, and I love the way you were doing it. How many cases? So forgive me, and if you weren't there and you don't know what, but how many cases did you get through? How many cases did you discuss or cover in the board meeting yesterday?
We only really want to do. So for the first example was if the source was stationary, and then the second situation is if the source was moving away from the river.
So you did those, okay. You did two cases, you're saying one, yes, good job. Oh, nice positive reinforcement, Charlie. Yes, okay. So you said, and yes, that was good. Although the audio cut out slightly for a moment. So you did you did source, stationary, receiver moving away, and then you did receiver stationary, source moving away. Is that correct? Is that what you just said?
Source stationary and receiver stationary. And then the second one was receiver stationary and source moving away.
Oh, I see. Okay. And when you did, so you did a case where the source and the receiver were both stationary. So nothing happened there, right? I mean, that was like a control case, sort of. Is that correct? Like,
yeah, it was kind of like to understand the the premise.
Cool. That's pretty smart of him. Okay. Thank you. Maybe remind me if you feel like it. I'm just intrigued. I don't know if you're going to get to the other cases with him or not. I'm not sure what he intends, but I'd be curious next. I mean, you may be shifting gears entirely in the lab next week. I mean, did he indicate whether you're going to get to the other cases with him or not? And the answer certainly could be not. I mean, but
I don't think so.
Yeah. Okay. All right. So remind me maybe next week if you feel like, I mean, because it's so interesting. Truly, it may not see. I don't know if it seems interesting right now or not, but there's a lot of like surprising implications in the Doppler effect once you look at once you start comparing a number of cases. Like, and I literally mean surprises. Like you'd think it would just start being like a repetitive pattern or something, but it isn't. And as long as you are doing that with him in the way that you're doing it, I'd be very, and I don't want to like spoil any surprise or anything like that, but so maybe next Tuesday, or next Wednesday, I mean, we have break, of course, but next, if anybody remembers, this is not a big deal, but I'm just curious, again, just because like things seem to happen in your class that are intellectually exciting to me. So if anybody who's listening now, any of you, if 2 weeks from now, when you come back and then you've had lab, maybe just remind me the next day that I'd like to hear about what you did in lab on the prior Tuesday. So either you will have done an electricity lab, which is totally fine and often the case, like in 2 weeks when you have lab, you may well be doing electricity, which is what I'm going to get back to talking about today. And that's fine if that's it. Or you might do more with this Doppler effect thing. Either one would be fine. But basically, I'd like to know from you guys what happens next Wednesday, because depending on what happens, I might want to make a comment or two about the Doppler effect when all dust is settled. I don't know if that makes any sense. You can see why I'm ending class early today, but okay. But very cool. I'm very glad I saw this yesterday. And again, I mean, I'm sure you all think I just give compliments all the time just because, but it's not true. And really, every time I walk into your room, your lab room, I mean, I'm really genuinely moved and impressed with how like sort of just alive and engaged all of you seem. And I really mean that. And it is a credit to him as well. I mean, it's a credit to all of you, but not all lab groups always feel that way. And but I'll say the last thing too, just as a, I walked in, and I know some of you weren't there, so you don't know what I'm talking about, but it applies to you. I mean, I've been there more than once. When I walked in yesterday, and I sat in the back for like 5 minutes. And then, one of you said, oh, and you asked me a question. I was not lying at all. I was literally telling the truth when I say I was absolutely paying attention. I was riveted for 5 minutes, but not to one single physics word you were saying. I was just watching everybody's like body language and the way you guys were talking. And I mean, for real. So I didn't hear the physics at all. And I was also, I mean, to be honest, I sort of deliberately try not to pay attention to, because it's your class, not mine, and it's his class, not mine. So if I get too involved, then I can start like messing with it. So I was just so like, oh my God, this is like such a real class. It's the way a physics class is supposed to feel. And not all classes feel that way. Not all physics classes feel, to me. Anyway, all right, what's the question? Are we good? That would be great. This is in the direct chat, but are you ever going to get a Professor Wu Johnson collaboration? God, I would love it. And I hope so, but I don't think so. Well, first of all, you guys are done anyway in a month. So, I mean, believe me, I would love it. But I don't think so, sadly. Okay, that's funny. All right, Nicholas, not that you needed to, but you totally redeemed anything that you might have needed to redeem in the last 20. Okay, that's it. Yeah, no, I know. It's so sad. Okay, but this is why we can't form emotional attachments, because they always crush our spirits in the end. Okay, just kidding. All right, so let's do a little physics here. This is okay. No, all right, okay, physics. Okay. I'll tell you what we're okay. I'm going to remind you. Whoa. Huh. I don't even, I can't even, what Gabriella just put in the, I'm like almost going to cry. Don't worry. First of all, you're going to be, see, this is the whole thing, this is the thing of being a teacher. You guys leave us before we leave you generally. I mean, you're going to be gone before any of this is relevant, and I'm going to be the one crying, but, and no, you're not losing me, but I know she's half joking and also, and half, but no, I mean, the attachment I feel to, well, okay. I mean, wait, I don't even get, no, and it's not, wait, I'm not even sure I get, no, for what it's worth, and yes, I'm getting distracted. I'm supposed to be talking about physics today, but you don't know. I mean, yes, you do know. I guess you do know, but no, I am so blessed to have these people like Wu and Walters or whatever, and it's crushing to me that, I mean, they were going to leave eventually. That is the way it goes, but I didn't expect it quite to go like this, but, and it's all in the love. I mean, I hope you guys know, I mean, Wu is in China, but we speak on the phone pretty frequently given the time difference and all that. And Walters, I basically hang out with him every Monday night before I come see. I mean, he'll always be, I love these guys. I mean, I am so blessed to have had them, but that's funny. Grab proof. That's funny. And not to put too fine a point on it, I hope that the replacements for Walters and Wu someday soon are some of you people. And I'm not kidding about that. I mean, where do you think they came from? Okay, that's funny. And I get that, which is really sad that I get that. But no, that's the thing. They're not breakups because it's still all the love, and I would do anything for the end, but it's anyway, oh my God, you're killing me, you people. Okay. But no, all right, see, oh my God, yodel, okay, all right, God, it's just not fair, because I didn't have the benefit of an early age, I didn't have the benefit of a youth, all right, I'm not even going to say this. You can't do this to me. I'm too vulnerable right now. All right, I'm doing some physics here, whether you like it or not, whether I like it or not. So recall. Luckily, the physics I have to do is okay, here's the deal. What I just wrote on the page here, what I wrote on the page here, this is supposed to be recall from 2 days ago. I'm just reminding you of two equations from 2 days ago. Well, one of which you've seen before, many of you, last semester or in high school or whatever. But I want to talk about I know I gave you these equations 2 days ago, and I know we have to go farther. We have to do things mathematically with them and all of this. But today, I want to talk a little bit about their implications. Okay, so this is actually going to be for good or for bad. Once I get going here for a few minutes, it's going to be physics, but it's going to be a little bit more Englishy. It's going to be one of my rants, basically. This is going to be a little bit more Englishy than mathematical for good or for bad. Okay, so bear with me. I want to remind you that these two equations here, first of all, note, so the top one is the gravitational force between any 2 point masses, right? That's what we said 2 days ago, and stop me if we didn't. Then the bottom one is the electrostatic, the electrostatic force between any 2 point charges, right? One's from like the mid 18th century, one's from the mid 19th century. Both of these, and you notice that both of them have very, very similar, if not identical, mathematical forms. That is definitely one of the things we're trying to emphasize here. Like when you think about how point charges, as in protons or electrons, attract or repel, whatever you're trying to visualize, you should try to visualize something very akin to how 2 point masses anywhere in the universe attract, right? The whole phenomenon, the interaction between point masses is our model for the interaction among point charges. And the only reason I think, by the way, that one of them is a little bit easier to picture than the other maybe is just that one of them has to do with masses, and masses are a little bit more macroscopic or palpable or tangible or accessible to the mind. Like to picture a point mass, you just take a mass of any kind and shrink it down to a Euclidean point in your mind. So you picture like a little fragment of a brick or something like that, and that's a point mass. Now, a point mass is very small. It's a little abstract to picture because you're picturing some amount of mass that's taking up almost no volume. Okay, so there's a little bit of an abstraction, or an idealization or an optimization, but it is an abstraction. It is an extrapolation from something with which you have direct daily experience, mass, right? Okay, so in the top equation, we're asking you to take any bit of mass, shrink it down to a tiny Euclidean volume in your head, put it over here, put another one over there. And what we're asking you to realize is that those two masses, wherever they are in the universe, whatever size they are, whatever is or is not in between them, they will automatically, necessarily pull on each other. Like one will pull on the other and the other will pull on the one with a force measured in newtons that is directly proportional to each one of their masses and inversely proportional to the square of the distance between them, right? So we're saying both, we want you to picture that all bits of mass everywhere in the universe automatically pull on all other bits of mass in the universe, right? And I'm not saying, but let me say, I want you to picture that. I want you to believe it or know that it is a piece of physics. I'm not saying I want you to understand it or even think that it makes sense yet. I'm not saying that. Like if you're saying like, I get it, but I don't get it, that's fine. In other words, if you're saying, well, I can accept what you're saying, but that I'm not, if you're asking me to see how it's reasonable, I don't. Fine. I'm just saying it appears to be true that all bits of mass, or it appeared to be true to Newton, when he put together data both from falling objects that fall near the surface of the earth and objects in the heavens, i.e. planets and moons and stars and orbits and eclipses. When he put together all that data and realized, oh, the same thing that's going on up there mathematically seems to be the same thing that's going on down here. It is on I always say this wrong. It is in heaven as it is on earth, is what he's saying, and what Galileo said. Oh, there's one law that seems to govern how all things pull toward all other things. And the law is that top one, right? So we're saying on the one hand, picture or recognize that according to physics, all objects of mass pull on all. Oh, sorry. Okay. Picture that all bits of mass in the universe pull automatically on all other bits of mass, but also picture or recognize, yeah. You can hear that texting right now. Actually, do you want to know the truth? It's the Walters, both of the Walters texting right now. I forgot to put on focus. I'll put on focus, do not disturb in a moment, sorry. But, you know, they should get through anyway because they're favorites, right? Okay, yeah, I am totally in trouble. No, they're actually, anyway, I'm always in trouble, but I was born to be in trouble. But so the top equation is asking you to picture that all objects are, but also it's asking you to picture, and this is important, this will become important in a couple of minutes, it's also asking you to picture that it's a quantitative relationship, that there is a precise, predictable, numerical extent to which one object pulls on another or another. Yeah, that's the only kind and the only source, that's right. Okay, so I want you to understand that the top equation is saying a qualitative concept and it's saying a quantitative description as well. Then the bottom equation, doing the same thing, just taking it one, it's applying it to the world that is one slight level harder to picture, at least for me. That is, it's saying whatever you believe about bits of mass, now I want you to believe that also about bits of charge. And when we say charge, what we mean is we want you to picture protons and electrons. So that's one level more abstract because of course you never see protons and electrons in your daily life, like, or not, you know, I get that. So in the first equation, we asked you to take things that you already have experience with and then extrapolate, shrink them down to a really tiny level and picture how they interact. Now we're saying, all right, picture stuff that's already at a tiny level that we've already sort of asked you to make some leap of faith in embracing in your early chemistry classes and so forth. But we're saying this stuff that you've come to somewhat accept in your mind as being somewhat of a model of reality, these protons and electrons, now those things that were already shrunken down in your mind, already tiny, we want you to realize that they are also interacting in this same qualitative and quantitative way. Okay, that's what we're saying so far. So charges attract and repel each other in the same way that masses attract each other. With that same mathematical predictability, and that literally the same mathematical form. That's what we're saying so far, right? Pause for a second while I do turn on the do not disturb because it's driving me crazy. Sorry. I should just have there should just be a setting on my thing that just says like, it just blocks out other things and just says warning, professor has ADHD or whatever. But okay, and I say that with all due respect to me and everybody. Okay, so we've got masses, we got charges, masses, charges. These two forces are known as fundamental, as opposed to the force of friction, or as opposed to the force of tension, or as opposed to the normal force. These forces are known as fundamental in that they happen automatically, right? That you don't have to, if you're a bit of mass, you don't have to do anything to pull on another bit of mass. You don't have to reach out and grab. You don't have to enact some activity or event, right? You don't have to deploy a mechanism. And I'm not being sarcastic, and I'm not trying to be silly. Like, as opposed to tension, like for the tension in a rope to actually pull a fish or a lobster, actually the rope has to go out and touch the lobster. Like, no joke. Like, for tension to be exerted on an object, two objects have to be in physical contact. Something actually has to happen. Ropes sitting around don't automatically exert tension. So tension is not a fundamental force. Fundamental forces happen just by virtue of existence, or put another way, and this is where I want to go with this. Put another way, both of these forces, both of these above forces are known as action at a distance. I mean, you may have heard this term before. I can't get enough of it. All forces are interactions. All forces are interactions, like we said Monday, interactions between pairs of objects. But most forces, at least on the macroscopic mechanical level or context, seem to involve contact interaction. Most forces seem to involve an interaction that is material, that involves touching. These two forces happen at a distance, which is actually a very well chosen phrase. When we say that gravity happens at a distance, or when we say that the Coulomb force, the electrostatic interaction, happens at a distance, we really do mean at a distance, because what we mean by that is like one bit of mass pulls another bit of mass, regardless of what's in between them. There could be nothing in between them. There could be empty space in between them, and they'll pull on each other, which already is kind of interesting. Like, right, again, they don't have to touch. They just automatically pull through empty space. Or you could put stuff in between two bits of mass. You could put a table in between a bit of mass and the floor, or you could put a table between a bit of mass and the center of the earth. And the center of the earth is still pulling on the bit of mass. I make no mistake, the table is now also pushing up the bit of mass. So I'm not saying the bit of mass will fall, like the table can support the bit of mass, but you notice when you put a table under like a object, if I put a table under this object, notice the object doesn't go flying up. It just sits there. What? Because the table is supporting it, meaning the table is not getting rid of gravity. Let's just be very clear on that for a moment. When I support a glass on a table, the table is not getting rid of gravity. It's just adding another force that's counteracting the force of gravity, right? mg is pulling down and the normal force on the table is pushing up. That's actually an important point, meaning that you can't block gravity, right? Gravity happens, whether it's through empty space or through matter. It just happens. It doesn't need the matter. It doesn't need physical touching to happen, but nor does it get blocked by matter from touching. That's pretty wild. That's part of what we mean by fundamental. It just happens, and there ain't no need nor thing you can do about it. Now, that's the same thing with the electrostatic force between protons and protons and electrons and electrons and electrons and protons. Again, by the way, sidebar, I mean, I keep just assuming this. I understand the one difference between electrostatics and gravitation is that charge seems to come in two varieties, where mass seems only to come in one variety. That's certainly interesting, and it certainly will affect our problem solving and stuff. Like electrostatics can be attractive or repulsive, whereas gravitation can only be attractive. That's certainly the case, but that's all that is. That's a difference. And in other words, that's why one has a minus sign and the other can have a plus or minus sign. But so I'm not saying they're the same. They are different, but they work mathematically exactly the same. Notice, in other words, if I've said anything so far, and I barely have, I'm saying so far, notice that there's like this interesting thing going on where we have some of these forces in the universe. We have some forces that we've discovered in physics that seem to happen through a distance, and those forces seem to always be sharing this common mathematical form in this. Like, it seems like a pattern here that may be inviting some kind of explanation, that a force that happens at a distance apparently seems to depend somehow, for some reason, inversely on the square of the distance between the two objects. Interesting, just like note, interesting, right? Now, I said before, now I'm really trying to stress here that these things are true. I'm also trying to stress that I've not argued that they make sense. I'm just saying that they seem to be true. Let's talk about sense for a minute. Let's talk about comprehending these. Newton, Okay, the top law is Newton's, right? The bottom law is Coulomb's. Again, not coincidentally, very similar law. One about masses, one about charges. Now, what I want you to know is that Newton comes out with this law, the gravitation law on the top. And even though Newton is a hero to many of us, to anybody who does physics at some level, views Newton as their predecessor or their teacher, their hero. But of course, Newton himself had teachers and heroes. Not only the ancients, but I mean, Newton, for example, had a mentor that many of us have not heard of outside of this context, a mentor named Richard Bentley, who was a don at Cambridge, like in other words, like a big professor, residential professor at Cambridge, who was the mentor to many people who came out of Cambridge and who later, became famous, such as Newton. So you don't hear about this guy very much in other contexts, but the point is that this guy, Richard Bentley, was a man that Newton would go to for advice or counsel or wisdom. At the time, around the time that Newton came out with this idea about gravity, about universal gravitation, about this action at a distance, this equation at the top, a letter, actually a series of letters, but one in particular, yeah, super easy. Oh, that's funny. Yeah, well, I guess. Wait. Oh, that's funny. I didn't even catch the thing about faves. Yes, no, you are my fave, but they are my faves. Whatever. So the time Newton, so a bunch of letters were written to this guy, Richard Bentley. Remember, he's like the hero to the heroes. Again, we don't hear about him much today, but he was in the background, but he was a hero to the heroes. And letters were written to him, I want you to know, at the time of this universal gravitation theory came out. And if you know this story, keep it to yourself for a second, or just roll with me for a second. Letters were written to Bentley, appraising or evaluating this new theory of Newton's, this in sort of pre-publication form. And the letters were somewhat critical. There were letters written to Bentley about this theory of Newton's, and many excerpts from some of the letters have survived and have been reprinted and requoted to this day. And one such quote from one such letter, I actually put in your Google Classroom about 5 minutes before this class, just so you have it for posterity. And I want you to, you can pull it up right now if you see it or whatever. Actually, I'll pull it up right now if you don't mind. I want you to see, because this is really worth noting. So what I'm about to show you is a critique. It is a critique of gravitation, of Newton's universal gravitation. And it was written to Newton's hero, one of Newton's heroes, one of Newton's mentors, Richard Bentley. Okay, and I want you to see this. So hold on, I'm going to switch screens for a moment. Pardon me. Again, if you had, it's in your Google Classroom, so you can look at it yourself if you want. Yeah, okay, hold on. Okay. Okay. So this is on the topic of action at a distance. And again, if you may be familiar with this letter, and if so, great. I'm psyched. Keep your knowledge to yourself for a moment, if you can, just roll with this. But so this is an excerpt from an actual letter written to Sir Richard Bentley. And I'm going to read it out loud. You can follow along. You see it on the screen, but I'm going to read it out loud. So this is what the guy says. And I'm going to warn you that the guy writing this letter to Bentley about Newton is someone that you've heard of. It is someone that you all know. It is a scientist from the time. So he writes, "It is inconceivable that inanimate brute matter should, without mediation of something else which is not matter, operate on and affect other matter without mutual contact. That gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else by and through which their action may be conveyed from one another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it." Now, this is, oh, some of you are, okay, I think some of you are familiar with this, but this is really worth dwelling on to me. This is like one of my favorite things. Okay, so first of all, let's get this straight. When it says that last part, when it says, it is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking. Competent faculty of thinking does not mean that I have like, it doesn't mean faculty like group of professors, right? It means faculty, like facility, like ability, right? So he's saying, right? I mean, I hope it's clear to you, like, he is saying at the end, the idea of action at a distance is so absurd that no one who's remotely clueful could ever think about it, could ever think it, right? I mean, this is, I don't know if it's, if this weren't a Zoom class, I'd like to turn it to you in a way, and feel free to make comments if you wish, but I hope it's clear that this is critical, okay? This is not in support of the theory of gravitation. It is critical. I hope that's clear. B, it's scathingly critical. It's outrageously critical. He's literally, and remember, this is like the 18th century. This is when people were polite, right? Right, when college was easy and people were polite. This is like sophisticated language, but this is like, if this were a subreddit back then, like, how it would read. He's saying that gravity should be innate, inherent, and essential to matter is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He's saying this is preposterous, right? Or tell me if you disagree, but like, he's saying this is totally stupid. Anybody who has a clue would not think this. Now, I want to say a couple of things about that. First of all, let me try to flesh out for you why, okay? Because this is, and this again, this is a critique on gravity. The thing that I'm trying to teach you is gravity. And I'm not trying to, I am trying to mess with you a little bit, but I'm not trying to trick you. Like, we are learning gravity and it is right. As far as anything is right. And I'm not going to do backsies on gravity. I'm not going to take it back from you and say it was all just a joke. Like, it's true. But yet there is something very bizarre about the idea. And that's what this thing is trying to get at. Specifically, the idea of something, pulling on something else without touching it is very weird. Now, why? Now, and by the way, it doesn't escape my attention for a minute that you've played with magnets. I know you've all seen magnets, right? And magnets are the one example in life that we have not yet mentioned in this class of action at a distance. And magnets, the magnetic force or the magnetic field most certainly is an example of action at a distance. There's a reason we haven't mentioned it yet in this class, and that is the mathematical formalism for magnetism comes last in history, like it comes after all of this, and it is the most complex mathematically. But what I'm getting at is this. Oh, I'm sorry, there are things happening in the chat. I'm sorry. Wait. Oh, yeah, no. Wait, and by the way, and I'm going to keep ranting for a second, but whether oh, that's funny. Both Gabriella and Nicholas, even if they're 1% serious and 99% joking, or the other way around, like, I am going to spend a couple of minutes here trying to get gravity to hurt your head a little bit, like in a nice, playful way, because it should, because there is something crazy making about gravity. What I'm trying to get at is this. What we believe about gravity, or what Newton's claiming about gravity, is that every bit of mass is like a little magnet, right? Like, not literally a magnet, but acting like a magnet, in that it's automatically pulling or pushing pulling other things without touching, like magnets do. Why I'm bringing up the magnet examples, I want to remind you, yeah, of course, you've seen magnets before. Yes, apparently things can pull other things without touching, but let's get it straight. If you ever did play with magnets as a child, if you ever found them interesting as a child, if you ever did the thing of like taking a bar magnet over like a bunch of paper clips and going and watching as the paper clips move around, around the table if it seems interesting at all, why? Because it is, right? Because it is fascinating that something could actually pull or push something else without touching it. Kids know that that's wild. And the only reason that eventually we sort of get used to magnets and we sort of stop realizing or like basking how fascinating they are is just that we get used to them, right? Same idea with things falling to the ground all the time automatically. It starts to become such a part of our experience that we accept it at some level. But if we actually stop and try to do the physics or talk about the physics, we have to realize if we really believe that the earth is always automatically pulling on things without touching them, that is a very exotic thing to believe. Now I'm going to go a step further though. Maybe you're like, yeah, you're causing, maybe you're thinking, I don't know what you're thinking, but you might be thinking, yeah, sort of like, yeah, that was interesting when I was 5. But first of all, I have gotten used to it and like whatever. But second of all, yeah, I'm like, why are you making a problem when it doesn't exist? Like obviously magnets do work and obviously things do fall down. So what's the problem? But the problem is this. We might have all sort of gotten used to it qualitatively, but then Newton comes along and now puts some math to it. Now let's think about the math for a second, not in a detailed calculus way, but just the fact that there's math at all. That equation, think about this equation. The equation says not just that stuff pulls on other stuff through empty space without anything material intervening to mediate the interaction, but it says that the pull happens in a way that is quantitatively determined, precisely determined by properties of the two objects and the distance between. So think about this for a second. And I'm dead serious about this. Think about this for a second. According to F equals GMM over R squared, according to that equation, which doesn't exist before Newton, like things fell before Newton, but then Newton comes along and says, here's a mathematical description of it. Now, according to Newton, picture the Earth at some distance R from the sun. Or if it's easier, picture like a brick at some distance R from the center of the Earth, whichever one's easier for you to picture. According to the math, the Earth pulls down on the brick, or the sun pulls on the Earth with a certain number of newtons that is based on or determined by how far away the Earth or the brick is, right? Okay, like the pull is directly, precisely determined by how far away the two objects are from each other. Now, the sun reaches out and grabs on the Earth through empty space, according to this evidently, or the Earth reaches out and through empty space pulls on the brick with a certain number of newtons. So and then F equals ma. So then the brick starts falling towards the Earth, right? So then the brick is a little bit closer to the Earth, right? Or the Earth is a little closer to the sun, like a moment later or a millisecond later or a second later or whatever. Because of that pull, the Earth is now a little bit closer. So now it's closer. So now the R is smaller. So according to, if we now believe in this math, if we believe that we have a quantitative description for this pull, that means now that the Earth is closer to the sun or the brick is closer to the Earth, now the force adjusts. That's what we're saying, right? We're saying the Earth reached out, pulled a brick through empty space, like yanked it a little bit closer to the Earth, and then the Earth adjusted its pull strength based on the new location of the brick. Now think about that for a minute. That is a crazy idea. I'm not saying it's false. I'm saying it's crazy. Like, why? Because, and I'm literally not trying to make a problem where one doesn't exist, and I'm not trying to exaggerate. I'm also not trying to be anthropomorphic. But but think about this. If the brick got closer to the Earth and now the Earth is pulling harder, according to this equation, that means some way, somehow, the new information of the brick's new location somehow got transmitted to the Earth, right? The Earth was updated with this new with this update. I'm sorry, the Earth had to have been in receipt of the updated information regarding the brick's new whereabouts. Just like if the brick if like a pigeon flew by and pooped on the brick and now the brick is heavier and now the Earth starts pulling on it more, somehow the Earth evidently knows this. That's what we're claiming. And I don't mean knows it like consciously, like I'm not being an idiot. Like I don't mean that the earth like is now thinking about it, but I'm saying if we really believe the earth is pulling on the brick or the sun is pulling on the earth with a number of newtons that's precisely dependent on the location of the thing being pulled, that means when the thing moves, the new location has to be sent to the pulling object somehow. The pulling object has to be getting the new information about the Earth's new whereabouts if this equation is true, right? And when I say information, I mean it. I don't mean numerals. I don't mean like Sesame Street. I'm really not trying to be an idiot. I don't think that the brick is like sending like a styrofoam like 2, through space to the Earth. But that's a numeral. I don't think that's happening. But I do think the brick must be sending a number. It has to be. Builds on. Great question. Builds on. It totally meant to address exactly what I'm saying. And I'm going to read it, but builds on. Sorry, direct chat thing. But like, I'm literally saying to everybody, and I am trying to mess with your minds a little bit, but I'm not trying to trick you. I'm trying to show you something that's very powerful and very, very at the heart of the physics mysteries or the mysteries that physics tries to like deal with. If we believe that the extent to which one object pulls on another is quantitative and is based on the information describing the two objects and their relationship with each other, which is what we're saying here. We're saying two objects pull on each other with an amount that's based on how big they are and how far apart they are. That means every time they change their separation from each other, somehow they must both become aware of that because the pull that they're exerting on each other gets adjusted, right? So that means when something's falling towards something else, every new little moment or instant or millisecond or whatever you want to, every little new bit of time that there's now a new occupation of space, somehow a new bit of information must get sent from one to the other. Otherwise, like, how is the pull being adjusted? We're not just saying it's just a pull. We're saying it's a specific numerical, measurable pull, right? So I'm going to go just one step further, and I do see that it's 1 o'clock, and then I'm going to start ranting. But I'm really saying that if you really think about this, if you really think that GMM over R squared or KQQ over R squared has to mean that each M is in possession of the information regarding R, right? Then that means that as they move towards each other, at every single moment, there has to be an update of the information. It means the information has to be that's why they use words like, so that one body may act upon another at a distance to back. Sorry. Oh yeah, without the mediation of anything else by through which their action may be conveyed from one to another. That's what it's talking about in that quote. Like, how is the action being conveyed? How are the new numbers being sent back and forth through empty space? And think about this. And again, I don't mean it in a conscious human way. I mean, I'm a goofy guy, but I'm not that goofy. I understand we're talking about it scientifically, but scientifically, we are talking about objects that do things based on information describing other objects in other places. The fundamental question is, how does one object over here have the information describing an object over there, somewhere else in empty space? And the real reason it's a real question is because even if you're picturing, well, I guess the information is sent from one to the other. Maybe it's like sent as a wave or something. Is that why we've been spending this whole course on waves maybe or something? And if you're thinking something like that, good, you're in my class, that's good. But even if your brain is starting to go like, well, I mean, I guess the numbers are sent from one to the other, but then that rate, and good, if you are, something like that must be going on, right? But that we're not done, because if you think that, if we think, okay, I guess every time the Earth moves closer to the sun, I guess somehow its new location, its new position vector somehow gets transmitted, propagated to the sun. I mean, weird, but okay, I guess that's going on. Then ask yourself, does that take time? Does that take time? Like literally, does that take time? Does it take time for the sun to find out the new spot of the Earth? Because here's the deal with that question. Either it does or it doesn't. If it doesn't, that's really weird. And if it does, that's really weird. Like, I mean, again, not like, seriously, if it doesn't take any time at all, if it doesn't take any time, if the information just gets there instantaneously, well, then that means it doesn't matter how far away they are, it's just getting there instantaneously. That means all information can get all over the universe, like in no time at all. That means everything's always happening at once. If it doesn't take any time, right? If it literally takes no time, regardless of distance, that means distance doesn't matter. We can convey information from me to you in no time, regardless of how far you are. So that means the whole universe can communicate. That means everything's happening at once. That's bizarre. That can't be. Or it does take time. But if it does take time, does that mean that as the Earth is falling toward the sun, like every new place that the Earth is, there's a delay? Like it takes time for the new location to get to the sun. So there's a delay before the sun can deploy its new force and pull the Earth. So does that mean that everything that looks like a smooth movie of life is actually like a stroboscopic, whatever, like a, dance hall rave, like, yeah, and again, I'm sort of exaggerating, but I'm not. Like, how does this make any sense? The real thing I'm getting at, and I know that it's 106, what I'm saying is the minute Newton says, here's how it works, things pull on each other through empty space with a pull that is determined by how big they each are and how far away they are from each other. And it's mm over r squared. And then 100 years later, Coulomb says, oh yeah. And the exact same thing happens with charges. When Newton, so we have both those, they're like in our notes, they're things. When Newton says this, it's actually, it does invite at least a day of discussion on our part, or at least it's not a surprise in a way that at least one really smart scientist from the day, from Newton's time, writes to Newton's mentor and says, whoa, dude, what? Are you serious? Something's pulling on something else through empty space at a distance with nothing in between mediating the information. Let me put it one final way. If you've been paying attention to this course, the purpose of this course is that we are in this course trying to develop an idea of how immaterial entities move, right? I mean, this was the thing from last Monday. The whole point of the course is that there's just unthing emotions in the world. There is information flow, not just material trajectories. But everything we've said in the course so far about information flow, about waves, requires a medium. That's why you're obsessing about it with Johnson, by the way, even though like we're done with waves here in the lecture. The reason you're still like obsessing over a Doppler effect with Johnson is because it's the Doppler effect. I mean, we'll get more into it next, is a whole way of actually really forcing our attention toward the role played by the medium that seems to be required for any pulse or ripple to go from one place to another. To send a sound wave, you need air. Right. So what this guy is saying here when he writes to Sir Richard Bentley is, whoa, there's flow from the sun to the earth through empty space. Like there's no medium in empty space. And you're saying things are pulling and pushing each other and sending information updates, possibly in real time, possibly not, in empty space. Are you crazy? Now it's 1:10. We are going to end early. Here's my question. I hope you kind of get what I'm getting at, but here's my question. The guy that wrote this letter critiquing Newton, the guy that wrote this letter to Richard Bentley, Newton's mentor, the guy that wrote it is actually someone you've heard of. You do know who he is. He was a scientist that lived at, or what we would now regard as a scientist, that lived at the time of Newton. If you literally actually know, because of some outside, because you've seen this before or whatever, then maybe keep it to yourself for a second. But let me ask, is there anybody in the room who literally does know who wrote this letter? I mean, have you heard from another class or anything like that? I'm looking at, and I'll probably stop. I'm going to stop sharing it for a second just so I can see all your faces. And we will stop soon, like I said, but I'm going to stop the share. Stop the share. Okay, there you are, and stop. I'm looking at your face. Okay. So does Okay, just do me a favor. Just we're gonna wrap up soon, but just give me like a thumbs up or like some emoticon thing. Just if you're still with me, if you're like still paying attention, you still like understand more or less. Thank you, awesome, Celine. Thank you, Mark. Oh, that's a lot. Thank you. Okay, great, Lobster. Okay, great, awesome. Thank you guys. I totally appreciate it. All right, so now you can put them down. I love it. I love looking at all the different skin tones too. It's so interesting. Okay, it's like an emoticon Crayola box. It's like a melting pot of Bitmojis. Now I want to ask, does anybody have any guesses or any thoughts about or knowledge of who actually wrote this letter? It is a sign, it is someone you've heard of. That's the thing. It's not easy to guess, but it is someone you've heard of. Does anybody want to, or no? Should I? Oh, somebody know. I could tell someone's smirking. I think she knows, maybe. Are you smirking? You can tell, or do you know? No, you don't. Okay. How'd you know I was talking about? No, okay. You forgot. All right, that's fair. That's fair. Okay. Does anybody, should I just tell you? Or I think it's worth knowing who actually wrote this. And you literally don't know. You guys, no gatekeep. I don't even know what that means. I sort of do. Wait, no gatekeep. But what does that mean, actually? Does that mean spoil? What does gatekeep mean? I should tell you or I shouldn't tell you? Okay, but the only problem is if I don't tell you, then I can't I can't end class because you got to know before. But okay. Oh, she. Oh, wait, how can I go against she? She's it me. It's gatekeep, withhold information. And thank you, by the way, for not being a gatekeeper on that, Mark. Oh, that Woo wrote it. Okay, that's hilarious. First of all, that's hilarious. Second of all, thank you for explaining the withhold information gatekeep. Okay. Here, I almost do want to gatekeep because it's worth it. It's worth. Of course, but the problem is these days I can't even hold people in suspense over things like this because like everything is Googleable in life anyway. But here's the deal: since I do want to let you go early, and you all are with me, right? You've been following. So this is a scathing. That's a really good guess. Honestly, let me say this quickly too. Honestly, Nicholas's guess Hook, it's about the best. It's not right, but it's probably the best, smartest guess possible because Hook was a contemporary of Newton's. That is true. You have heard of him. And it's true that Hook and Newton disagreed violently. Not violent, I mean, they didn't like literally fight, but they had deep disagreements over super important physics matters. So that's a really reasonable guess, but it isn't actually Hook. So I'll tell you who it is. Now you're going to say that when I tell you this, you're going to say I'm gaslighting or something. But the person who wrote that letter was Newton. Okay, like literally, like truly. Newton wrote that, and he wasn't joking. Newton privately wrote that letter to his mentor about his own theory of gravitation, which was subsequently published and which we use to this day, and which is the theory or the laws or whatever that put men on the moon, no joke, in 1969. Like, let me get this straight. Even by 1969, we had Einstein and all these later developments that someone asked me about in the direct chat. All these amazing things happened later, but still, it wasn't Einstein's equations that put people on the moon. It was Newton's. Like, that's how good and real and right they are. Okay, but right. Okay, yes, no, and you might think, okay, maybe so. I mean, I see what Nicholas is saying in the chat, but like literally, this is one of my. I am trying to like mess with your minds, but no, I'm not trying to mess with you. I'm not trying to like, God, you guys, aren't I cool and aren't you? No, I'm trying to say, look at how physics gets us. Like, here's the deal. Well, yeah, this is a little bit anti, but really, to me, it's such a climax because this man, this is what it means to be the founder or among the founders of scientific thinking. I want you to know that when Newton wrote that letter, it represented a series of thoughts that ended up driving him crazy to his dying day. He went crazy over this. He wasn't kidding around. He hated his theory of gravity. He published it. He believed it, but well, I don't know if he believed it, but he knew it was right. We use it to this day. It's revolutionary. It's super predictively accurate. But he hated it because it didn't make any sense to him for reasons that legitimately don't make sense to a lot of us. Well, I mean, maybe. And obviously, and as he did say, if he was able to think such great thoughts, it was because he stood on the shoulders of giants. I mean, he gave a lot of credit where credit was due and a lot of credit was due. But here's the real deal. The real reason I tell this story is, to me, there is a fine line between genius and insanity, as you know, if you know Walters. But But like, no, what it really is. No, I mean, it may sound like that. And I know you're half joking, but and also, by the way, he kept a lot of this stuff in his attic for a long time in private before it got out. That's a whole other aspect of the story, but it's the reverse of him. What it is, what it is that this is where, well, okay, that's probably true too. What it is though, is this is really where science breaks off from philosophy. This is where science really starts to become its own way of thinking, because this is where it starts with Galileo, but it explodes with Newton, because what Newton is really saying to everybody is, this seems to work. This equation seems to describe the data and seems to make predictions of new data that are true. And it's true. Like, it predicted like the rate at which objects would fall. It predicted eclipses and conjunctions of Mercury. Like, it predicted astronomical events with remarkable precision. And to this day, even though we have developments and even more precise things, to this day, the level of precision with which F equals GMM over R squared makes predictions, like says things that are going to happen that then do, the level to which it stands up to scientific, predictive, quantitative, reproducible accuracy is astounding. But it doesn't make any sense, meaning that Newton was willing to suspend it's simultaneously incredibly arrogant and incredibly humble, the way science is supposed to be. Newton is saying, look, I thought I had a concept of the way the world should work. I feel like if things are going to communicate with each other, they should have to touch each other. There should have to be a meeting between. I've got all these ideas in my head, these intuitions, these biases about what would make sense in the world. And I've got these hypotheses, but then I've got data. I've got sensory evidence that is reproducible under controlled circumstances that says stuff that then allows me to make predictions about future stuff. I've got equations that work. I don't understand them, but I'm here to say I'm not God. My understanding is what I'm trying to develop, not what I'm trying to put first. I'm trying to put the data first and glean my understanding from that. So Newton's saying, I totally don't get it. And it's driving me crazy. And it did drive him crazy. And he eventually wrote letters where he said, later in that very same letter, he wrote something like, how this should work, I leave to future generations. He literally said, and the future generation that eventually picked up the ball and did something with it was Einstein. Like, it took until Einstein for someone to actually connect certain dots and say certain things about how this could make sense. And by the way, since we are going to leave in 2 minutes, by the way, the big answer to how any of this could work, the thing that we're going to deal with for the rest of the class, is apparently we believe as physicists, since we really do join in Newton saying information cannot just go through empty space in no time from one object to another and just do that. That doesn't make, so what we end up believing is that the sun does not just pull on the earth. What we end up saying is the sun creates something called a field, which is all the information describing the sun's mass and the sun's whereabouts. And the field, this is what we believe to this day, that the sun, the minute it exists, puts its information everywhere out in the universe in something called a field. And then the earth is in the universe and is somewhere in that field. And the information's already there, and the earth receives that information. And so what we say today is, we don't say the sun exerts a gravitational force on the earth. We don't say the proton exerts an electrostatic force on the electron. We say the proton creates an electrostatic field, and then an electron is in the field, and the field exerts a force on the electron. Now, if we hadn't, and I know we are going to leave in a minute, but if I hadn't just said this whole thing about the Newton's letter and and maybe it bothered you, or maybe you think it's boring, whatever you think, if I hadn't said all of that about the letter and Newton, all that, I could just start this class in the way that many classes are. I could say, now we're going to learn about fields. Here's how fields work. The sun creates a field, the field exerts a force on the earth. Like, and that's true. That is what we're going to do. I could just say that, but then you would all be very, very right in thinking, wait, what? Field? Wait, what? What you're not telling us to believe, like there's just like information in the world. You're telling us to believe in this immaterial weirdo thing called a field. Like, where'd that come from? Why are we going to believe in that now in a science class? And when and you'd be right to object and to be like, have your brain go bump in the night, like field, what? I'm here to tell you, we're going to deal with fields for the rest of this class. A field is the information of describing a given object existing everywhere in space the minute that object exists in space. Fields are funky. Fields are immaterial. Fields are abstract. Fields are a little bit hard to believe in or accept if you're just introduced to them out of nowhere. But if you understand that a field is our best possible working answer or temporary place-holding answer to the question of how the heck does the information of one object get to another object through empty space? Well, once you really get your mind around that question and realize that it sent Newton to his grave, we say, well, we've got somewhat of an answer. It's not a great answer, but it's an answer that works. And the answer is there is something in between the sun and the earth. There is something in between a proton and an electron. It's not material, but it does contain the information and it does allow for the information to be flowed through. And it is kind of like a medium for waves, and it's called a field. So from here on in, and we're going to go from here on in, one object exerts a force on another object. I exert a force on you. But when it comes to interactions that are through a distance, when it comes to fundamental forces, we believe in a third agent. We say, I, by myself, create a field. You land in my field. The field exerts a force on you. A field is to fundamental forces as mediums are to waves, in a sense. The field is the sea of information that exists between objects that allows the propagation of their facts to occur. Okay, we're going to end with that, and I have to go. I know it's late for being early, but it's early for being late. But that's the deal. It was Newton. He wrote it. Einstein did more with it. Thank you. I will bring lobsters. Okay, thank you guys for paying so much attention. I hope that made some sense. Okay, I will bring the plushies. See you guys later. Oh yeah. Thank you guys. Oh yeah, the second camera. Right. Okay, I'm gonna go. Thank you guys. I'm gonna go if that's okay. Okay. Thank you. Thank you very much. You too. Thank you. Oh yes, have a great break. Yes, have a great break. You too. Good point. Thank you. Okay, bye guys.